In this video, we're going to talk about sorting. So in the last video, we talked about searching, and we made the point that searching is much easier when we have a data structure that's already sorted. Okay, so when you're searching, if you know that the data structure is sorted, you can start in the middle and do a binary search and basically exclude half of the remaining half of the remaining data every time that you try to move things around. Okay, so that's an important concept. So this idea of sorting is one that's important for us. Okay, so we're going to talk about some different sortings. With sorting, what you're concerned about is the efficiency of the algorithm, and there are two basic categories we're going to have here. Okay, we've talked before about big O notation, which giving an input size of n, on average, how many steps do you need to accomplish the task? Okay, so sorting, the first algorithms we're going to talk about are big O of n squared, okay, which is to say that if we were to have 10 elements, to sort it would take 10 times 10, or basically 100 iterations through the loop, okay? The last that we're going to talk about are at the big O of n log 2 of n, okay? And again, log 2 of n is less than n, so this is going to be less than n squared, okay? So it's going to be a more efficient algorithm, okay? In fact, it turns out in an algorithms class, you would get into proving this, that this n binary log of n is the fastest or the most efficient possible comparison-based algorithm. Okay, so again, beyond the scope of this class, but just know that the ones we talk about at the end are going to be the fastest that they can be, okay? So the reasons, you may be thinking, well, why do we do the slower ones or the less efficient ones, okay? The ones that are at big O n squared tend to be easier to code, okay? So it really comes down to, if you have a small data structure that you're going to be sorting, then you don't necessarily need the efficiency or the complexity of the others. Okay, they're also straightforward to start with. So there are many out here in this category. We're going to talk about a couple. The first is called an insertion sort. Okay, in the insertion sort, the basic idea is that you start with one element of the list. Okay, so if you've got an array of, what do we have here? 6, 8, 2, 14, 21, 3, whatever it is, okay? If we start with just one element of the array, then it's already sorted, right? You can't have one element out of order, okay? So the next step then is going to be to add another element for consideration, okay? And you're going to make sure that this new element is bigger than the one you had before, okay? If not, you're going to swap it, okay? So now, and this happens to be sorted, okay? So we're good there. We now go to here, okay? And we see that we're now out of order, okay? So we have to first swap the 2 and the 8. We're still out of order, so then we swap the 2 and the 6, okay? And now that much is in order, okay? And you're going to keep doing this, basically, is how this goes, okay? So this has an n squared algorithm. You can do this on arrays with no problem. And it's, you know, it's not a horrible way to go, okay? I'll mention in passing the sort that everyone likes to make fun of for good reason, and that's a bubble sort. Okay, with bubble sort, the idea is that you, again, going back to this one that we have here, you're going to look at every 2 elements and swap the biggest one to the right, okay? So you compare these 2, you're fine. You compare these 2, you're not fine, so you would switch the 8 and the 2, okay? Those are okay. You would compare those 2, those are okay. These are not okay. So the 3 would go there, the 21 would go there, okay? So with a bubble sort, when you're at the end of the first run, you know that the 21 is the biggest, it's bubbled up, okay? But you've made a lot of swaps along the way, so it's not a great sort. So we're not going to go into any more detail on that, okay? But just so you know, that's why people make fun of it, okay? The insertion sort is just as easy and a lot more, it's not even more efficient. That's not even the issue. It's not the number of operations, it's the swapping takes a lot of memory movement that you don't need, okay? So the other one at the big O of n squared we're going to talk about is the selection sort. So with the selection sort, the basic idea is, if you have your list here, whatever's here, 7, 14, 3, 21, 16, 4, whatever, okay? So the idea behind the selection sort is that you're going to search for the smallest, okay, in our list, okay? So the smallest in the list, and we can put our positions here, we have position 0, 1, 2, 3, 4, and 5, okay? The smallest in the list here is going to be the 3, which is at position 2, okay? So we're then going to swap position 2 with position 0, okay? That's our first element, okay? Which is going to give us 3, 14, 7 with that swap, 21, 16, 4, okay? So again, we swapped these two elements, okay? We now know this much of the list is sorted, okay? So we're going to stop for that round, okay? We go to the next round. We find the next smallest item, okay? Next smallest item is this 4, which has 5 as its index, okay? And that's a 1 because we've moved that counter up, okay? We would now swap these two, okay? The 3 is still in the bank. We're going to add the 4 here. 7 stays where it's at. 21 stays where it's at. 16 stays where it's at. The 14 moves here. Okay, we now have progressed by 1. Okay, and you just keep doing this until you get just one element at the end, which would be the 21, but you'd be done there. Okay, so both of these are in the big O n squared, and they're not horrible if you have a small enough data structure. Okay? So again, if you do some math and think about things, and if you're in algorithms class, you come up with this idea that the best performance we can have is at the big O of n log n, okay? So the n squared are worse than that, so we know we can do a little bit better. So here are the better algorithms, okay? And this video, I'm not going to go through the code. The code is commonly available, but I think that understanding how the code works is time better spent, okay, in this video, okay? So the first one we're going to talk about is a quick sort. Okay, and what the quick sort does, okay, in a nutshell, it's going to be one of the divide and conquer algorithms. That's a class of algorithms where you basically split a problem basically in half and then work on each subsection, okay? The binary search that we did before is an example of a divide and conquer, okay? So the way it works, you're going to do an if here. If the list size is greater than 1, okay, so if it's equal to 1, then you're done. You can't sort a 1 out of list. We're going to do the following, okay? We're going to partition into 2 sublists, and we'll talk about the idea of partitioning in a second. I'll call these lower and upper, okay? And then we're going to quick sort the lower and then we're going to quick sort the upper, okay? And then we're going to combine back the lower and the upper to original list, okay? So, and I need to, for completeness there, stop that, okay? So let's look at this idea of a partition, okay? So partitioning a list is based on the idea of a pivot. A pivot is a value I'm going to use to divide the list. Okay, so for example, if our list were the following: 7, we have a 12, we have an 8, we have a 21, we have a 36, we have a 15, and we have a 23. Okay, and let's say I'm going to take the pivot to be 15. Okay, so when I'm done, I should have the following. I should have all the values that are less than 15 or less than the pivot. Okay, we're then going to have the pivot. So the 15 will be here. Then we'll have all of the items that are greater than the pivot. Okay, so in this case, we would have 7 over here. We would have 12 here. We have 8 here. We have 21 here. We have 36 here. And we would have 23 over there. Okay, we would then take and call this the lower, and call this the upper. Although note, 15 is in its sorted position. Okay, however many there are here, in this case 3 and 3 over here, we know that 15 is going to be in the middle. Okay, so some algorithms don't deal with that. You just deal with the other parts and leave that where it's at. Okay, so it depends on how the algorithm is written. Okay, but also know that this was a contrived pick and that 15 split it in half. It could also be that we're not going to get that good of a pivot. The pivot could be skewed a lot. Okay, oftentimes when you have access to that data, you could do something like take the largest element divided by the smallest to give you some idea of the pivot. Okay, there are lots of strategies for picking the pivot, but in general, the better your pivot is, the better the performance of the algorithm. Okay, so this is working again. We take our list that was totally unordered. Okay, at this point, we now have it semi-ordered. Okay, we can now work on this half and this half. We quick sort those as well. We partition those again. Okay, so we're going to keep moving through this process. Okay, so that's how the quick sort works. Again, the code is a little more complicated than you would get with a selection sort or an insertion sort. But if your data structure is big, then it's going to be worth it to get that extra bit of performance. Okay. The other sort we talk about a lot at this stage, it's also in Big O of nlogn, it's called merge sort. Okay. The merge sort works, I think visually is the best way. If you have a list, let's say of size 8, okay, it's going to divide it in half. If it can't do it exactly in half, it does it as close to half as it can. Okay, so each of these halves, we then have 4 there, and we have, no, that's the whole thing, 4 there, and we have 4 here. Okay, start with that line there. But you've divided those into half. Okay, the 4 gets divided into a 2 and a 2. These are done roughly, just there's no computation. It's the first 2 and the second 2. Doesn't matter their values. We're not doing any comparisons at all. We've yet to do a comparison. Okay. We then divide these up into 1, 1, 1, 1, and 1, 1, 1. Okay. Note that these are just of size 1. Who knows what's there? Okay. We then start combining them back. Okay. At this point, each list here is sorted because there's only one element to it. Okay. So let's actually, that was not helpful. So let's go back to here. Okay. So back to here, let's just put some data in here. And again, this is not really data here. Let's say we've got 17 here, We've got a 4 there. We've got an 8 here. We've got a 20 there. Okay, we've got a 10 there. We've got a 3 there. We've got a 22 here. We've got a 31 there. Okay. And again, those twos, the 2 here, just to be clear, sorry, I'm not being very clear on any of this. And I won't do all these. But this one would be a 17 and a 4. Okay. This would be a 17, 4, 8, 20. Our whole thing here would have been a 17, 4, 8, 20, 10, 3, 22, 31. Okay. So this is the where we're dividing them up in half. Okay. We're then going to merge them back. Okay. So we're going to create a new 2 element here by looking at both of these. Which one's smaller? We put the 4. Now that's done. Which one's, now there's just one left, and our 17. Okay. So we've sorted these back. Okay. This would sort to an 8 and a 20. Okay. This would sort to a 3 and a 10. So we're combining back together. Okay. This would sort to a 22 and a 31. Okay. So we're working the other way. Okay. We would now go and divide it into 2 4s. So that and that come into there. So we take the smallest of all 4. There's a 4. Get rid of that one. Now 17 is the smallest in this group. We look at this versus this. We get an 8. Okay, that's gone. We get a 17. We get a 20. This is the merging. Okay, over here, similar process. We get a 3 and then a 10. And then once you've exhausted both of these, you would need just to copy those over in that order. Okay. Now that's sorted again. Then finally, for this last bit, we would track the head of the list, which is the smallest. The smallest of these would go here. Okay, that gets wiped out. That's now the smallest. We compare the 10 to the 4. The 4 goes next. Okay, that gets wiped out. Now we're comparing the 10 to the 8. Okay, the 8 goes here. It gets wiped out. The 17's in there. Now we're comparing the 17 to the 10. The 10 goes next. Then the pointer goes to there. We get the 17 over here. It goes away. The pointer's now just with this last one. Okay. The 22 is next. Comes here. The pointer goes to there. And finally we do the, oh, sorry, that was not correct. That was a 20 over there. So at that point, he would have put the 20. When that's done, it would do the 22 and the 31 over there. Okay. So that's the idea behind the merge sort. Okay. And again, if you look online, there are lots of implementations of that in C++. So we won't go through the code. I wanted to go through the idea. Okay. And this one I think is a very visual one. And I think the idea makes sense, which I think is useful. Okay. The last sort we're going to talk about is called a heap sort. Okay. And the heap sort is going to deal with trees, and we haven't really got to trees yet, so we won't cover this in as much detail. But just to say that if we have whatever our array is, got 14, 18, 7, 21, 30, and 2. Okay. To turn this into a tree, we just do the 14, 18, 7, 21, 30, and 2. Okay. So that's how we would convert this into a tree. For it to be a heap, okay, it has to have 2 properties. Okay. The first property of a heap is that it's essentially full, which means that if there are any blank spaces, they're on the bottom row and they're to the far right. So in this case, this is what's missing. Here's our blank space. That's okay. If this blank space were anywhere else, then it would not be a heap. Okay. The other idea behind a heap is it's called the heap property. Okay. It's also called parental dominance. Sounds like a parenting approach. Okay. Parental dominance says that for every value, the value that the root is greater than the value of the children. Okay. So to check that, we'd have to start low. We start with the 7. Is 7 bigger than 2? It is. Is 18 bigger than 21 and 30? It is not. Okay. So we would have to basically swap it out. So the 30 were here, the 18 was over there. What I'm doing here is a process called heapifying. Okay. And then I would have to check to see, is 14 greater than 7? It is, but 14 is not greater than the 30. So 30 would go here, the 14 would go there. We then have to recheck this. This is no longer a heap either. So the 21 goes there, the 14 goes there. Okay. So now we've achieved a heap. Okay. And that we're essentially full. The blank spot's only over here. Okay. And also we have for every level, every parent. So 30 is a parent, 21's a parent, 7's a parent. Their values are greater than all of their children. Okay. So by doing this heapify, okay, we're able to bring the largest element to the top. Okay. So as a sorting algorithm, when we're done with that, when we're building our new algorithm, we know that the 30 is over there. Okay. We remove the 30 and we have to re-heapify. Okay. You have to promote one of them up. You promote up to 21. Okay. Which would then go to the 14 and the 18. You have to make sure that's still a heap. Okay. And keep moving from there. Okay. Turns out 21 is the next biggest number. So the 21 would go there. You'd remove that and go from that. Okay. So the steps here for the heap sort are basically to heapify your data. Going to remove the root. Okay. Call it the largest. Okay. You're then going to re-heapify. Okay. And that's the basic idea behind the heap sort. Okay. So a heap, when you think of a heap, like a heap of clothes, a heap is a partially sorted list. Okay. If it were sorted all the way, then a heapify would be a sort. Okay. But it's not. It's partially sorted. Okay. So I think it's interesting to note that two of the quicker algorithms, the quicksort and the heap, rely on partially sorted data structures. So to partition is to partially sort something. It's not to put it in total order, but it's to take some pivot and divide everything into one side or the other. Okay. So it's by these repeated partial sorts turns out to be more efficient than other ways to go. Okay. So that's an overview of the sorting algorithms and a little bit about the efficiencies. Okay. So hopefully that's helpful and a useful thing. If you have questions about it, make sure you let me know.